which is Steven's view on abstraction logic is all you need.
Yeah, so I'm working on Practal, which is going to be a system for practical logic. And so I'm very excited to tell you that abstraction logic is all you need. So I believe that abstraction logic can be a foundation for artificial intelligence theorem proving. And I think it provides a nice point of view to attack various problems like auto-formalization, machine learning, and so on. So I think it can really be a unified foundation for all of that. And at the core of abstraction logic is basically the question, how do we bridge the gulf between informal and formal mathematics? Right, so I think most of us here think, well, machine learning and LLMs are probably a big piece of the puzzle, and I think that as well. And probably a lot of people also think that it doesn't matter too much how we represent the formal side of it, like a dependent type theory or something like that. As long as we throw enough GPUs onto the problem, it might just work out, right? But I think looking at the formal side more closely is important. And so the question is, how can we come up with like a general way of viewing formal mathematics, of representing formal mathematics? And I think essential for that is that we have a logic that supports general binders and also a single mathematical universe in which all the mathematical objects live. So informal mathematics has this for sure. Like if we talk about mathematical objects, right, then implicitly we think, oh, there must be some space of mathematical objects. I mean, otherwise that term wouldn't really make sense. So general binders, what do I mean by that? Well, just that you have the ability to define new variable binding constructs, right? So universal, this is so the first existential quantification, universal quantification, choosing an X so that X is true, summing up a family of natural numbers, and defining functions. And in abstraction logic, you can represent it like that. I think it's pretty straightforward. You have these abstractions, exists for all, and so on. And I think it's pretty clear that going from left to right and going from right to left is not much of a problem. And I think this is also in opposition or a counterpoint to the previous talk, you know, where there's all this hidden structure in terms of types and so on. On the right-hand side, there is no hidden structure. Okay, what you see is what you get. There are no types hidden somewhere to make this work. And on the left-hand side, neither, right? So why would your formal language have that? And so when it comes to general binders, type theory has them. I think that's one of the big reasons why we use type theory, because it has general binders. And first-order logic and second-order logic kind of don't. They only have universal quantification and existential quantification. Yeah, so the second property, the single mathematical universe. Yeah, as I said, like, you have different mathematical objects. You can put them together. Here, for example, I've thrown them all into one list, a number, a Boolean, a function, and a set. And, well, first-order logic especially has that. Second-order logic kind of, I guess. And type theory doesn't have such a single mathematical universe. And it's clear why not, because when you're talking about functions from mathematical objects to mathematical objects, let's call this like just operations, right? And it's guaranteed that there are always more operations than mathematical objects. But type theory tries to treat operations just like mathematical objects. And so if you really want to do this, you run into a paradox. And the way that type theory gets out of this is it has this hierarchy of universes. But the problem with the hierarchy is, well, you know, how far do you go? Even if you like take the union of all of these universes, then you know, you just when you start, you can still not represent the operators on this unified universe as mathematical objects. It's just not possible. And that leads to all sorts of complications like polymorphism, sum types, and whatnot. Another example where a single mathematical universe is really nice is, for example, you can easily deal with undefinedness. So you just have a value in your universe that stands for undefined, or rather error, right? And then it's easy to say what x divided by 0 and then some other operations behind mean, right? It's just an error. And well, if you want to do this in type theory, then you come up with all sorts of strange constructions. And so abstraction logic has both. It has general binders, it has a single mathematical universe of mathematical objects, and the way it does this is it just acknowledges that operations are not mathematical objects, okay? So mathematical, they're not, but the problem then is, how do you talk about operations? Because they're not mathematical objects, but you need to talk to them anyway, and so you introduce operators. And operators are functions from operations to mathematical objects. And that's basically it. So I think abstraction logic can be a foundation for artificial intelligence theorem proving. And so why? Well, it has general binders, it has a single mathematical universe, and from this flow all sorts of good things. And especially it has a simple syntax, it has a very simple semantics, it has a very simple logic, and I don't think it's possible to have anything simpler. I mean, if you think of something, tell me. So as for the syntax, you have terms and you have templates. There are two kinds of terms, either variable applications, applying variables to terms, or abstraction applications, where you apply abstractions to templates. And a template just binds variables in a term. And the meaning of this is also simple. Variable application is just an application of an operation to mathematical objects. An abstraction application applies an operator to operations, and a template corresponds to an operation. So terms correspond to mathematical objects, and templates correspond to operations. And the logic is also simple. It's basically a sequence calculus. And so you have antecedents, you have succedents, and so pairs, you have a pair of collections of templates, and that's important, that this S1, Sn, and T1, Tm, these are templates, not just terms. And you can get a special case of sequence. These are rules, which have like exactly one succedent called the conclusion, and this one conclusion must be a term. This cannot be a general template. And formulas, a special case of a rule, it's just a rule that has no premises. And so basically a formula is just a term. And actually in abstraction logic, every term is also a formula. So on the left-hand side there, this is a complete sequence calculus, or let me rather say the sequence calculus. These are all rules. I think probably the most interesting part here is the cut rule. Where you can, if you have in your antecedents and in your conclusions, you have like the same term, and there might even be some binders in front of them, you can cancel it out. And the rest is just like weakening and assumption and substitution, stuff like that. And on the right-hand side, you have an example of a particular abstraction logic with 8 axioms. So, and what's special about this one is that all of these axioms are rules and not general sequence. And there's this theorem: if all of your axioms are rules, then the logic is complete. So, you know, no matter what kind of abstractions you have, in this case, you have only implication and for all and equality. So no matter what abstractions, no matter what axioms, if they're all rules, then it's complete. So I think that's great for machine learning, because it can adapt to basically all situations. So there is an implementation of abstraction logic, small one. It's a minimal prototype in TypeScript, and basically every theory is represented as a TypeScript module. And there's a book about abstraction logic that I've worked on. In the current edition, you can download it at this link, practal.com, WG5. And for today and for tomorrow, it's free. And yes, otherwise you can buy it on Amazon. Yeah, and well, take a look at it and see if it might speak to you. Okay, thank you.
Time for questions.
Yeah, I was intrigued by your handling of undefined mass, but I was also confused because I've tried that inequality, you fail because what you get is 5 divided by 0 is undefined, 7 divided by 0 is undefined. So 5 divided by 0 is equal to 7 divided by 0. Then you cancel the 0.
I haven't quite understood your reasoning. I mean, that reasoning wasn't on the slide there, right?
No.
Okay.
That was a problem I was encountering.
Okay, so then we can do it afterwards, but you say like, I mean, basically, if you have terms that the point of abstraction logic is that undefined, it's not really undefined, it's just one value that means error. And some operations might yield the error, right? And it's totally possible that on both sides of the equality, you can have error. And in those cases, the equality holds. But you had problems with this approach.
No, the question is, if I know that I'm just rephrasing, taking the liberty of rephrasing the question. If I know that 5 divided by 0 is equal to 7 divided by 0, then I can multiply both sides of the equality by this quantity, 0. I don't know what 0 is, I just know it's a thing. And then I get, by elementary cancellation, 5 equals 7.
Well, the basic question is what is 0 times undefined, right? What is 0 times error? And you cannot just apply arbitrary theorems like cancellation. You know, the cancellations must apply to the situation at hand. And I mean, 0 times undefined. It depends on how you define multiplication. If it's undefined, then I'm pretty sure the cancellation law doesn't hold. So you would have as a precondition in those. I mean, the cancellation law as a precondition has for sure that the argument cannot be undefined, right? So otherwise, the cancellation law will not hold.
I think maybe let's take this offline. Otherwise, it's fine. Let's thank the speaker again.